All right, so you've got this 8 kilogram object. You throw it upwards at 4 meters per second. Its starting location is 0.3 meters below the end of the spring. The spring itself is 0.5 meters long when it's at equilibrium, and it has a spring constant of 800 joules per square meter. So this is our initial situation. And we want to know how close can the object get to the ceiling. So presumably the object's going to get slower as it moves upwards. As it compresses the spring, it's going to get even slower still. Eventually, it's going to reach what final speed?
0.
Yeah, eventually it's going to come to a stop, reach speed 0. And of course, after that, it's going to bounce back down. But we don't really care about what happens as it falls. We just want to know how close does it get to the ceiling. So the final situation we're going to investigate is when the spring is compressed as much as it can be, and the object is at rest. So V final equals 0. And we want to know how close is that from the ceiling, how close is that to the ceiling at this point? So we want to know what is the final distance. So we know that the kinetic energy is changing because it's getting slower. We know the potential energy is changing because our spring potential energy is changing because the spring is getting compressed. And we know gravitational potential energy is changing because we have the object moving upwards. So if we list out all of those, kinetic energy is decreasing because the object is getting slower. In fact, we even have its initial and final speeds. Spring potential energy is increasing because the compression or stretch, either way, is effectively the same because x is being squared in the equation. But the distance from equilibrium is increasing. We start at, how much is the spring compressed at the beginning?
It's not compressed at all.
Right, so we say x initial is 0 meters. X final, in the end, we don't know how much it's compressed. So we're going to treat this as an unknown. And then gravitational potential energy, the object is moving upwards. Its height is increasing, so its potential energy of gravity is increasing. And that means we'll need to list initial and final values for y. And that means we're going to need to set up a coordinate system. We need some way of labeling y values. So we'll want to choose a location to call y equals 0. And this is where we got to be careful, because we could choose any location to call y equals 0, but some locations are going to make things much easier and others will make things somewhat more difficult. Initial displacement be 0.1 meters. No, I would just treat the initial displacement as 0 because the spring is currently at its equilibrium. And the problem does say some nonsense about how if there was the object hanging from it, then its equilibrium would be different. But I would just ignore that entirely in this case, because the idea of the equilibrium being different if an object is hanging from it is really only even relevant if the object is oscillating. In this case, we're not talking about oscillation. We're just having this object move upwards, hit the spring, and compress it. So I would just treat it as everything measured from equilibrium of the spring. In fact, since this point right here is equilibrium of the spring, it might be useful to just treat that location as 0. Because if we treat a different location as 0, we're going to need to set up some sort of conversion between x and y. X being how much the spring has been stretched or compressed, versus y being the height of the object. Although, what are we actually trying to find here? What's the question specifically asking for? We want to know what?
The distance from the ceiling.
In that case, if we're trying to find the distance from the ceiling in the end, it might make more sense to treat distance from the ceiling as y. If we're going to have to find some specific value, we have the option of how we set up our variable, we may as well set up our variable so that the value we're solving for is just the answer we seek. So let's just say y is distance below the ceiling, meaning we're going to call the ceiling y equals 0. So what would be y initial? What's the starting height?
That'd be negative 0.8.
Yeah. You start off at negative 0.8 meters. That is 0.8 meters below the ceiling. So that's our y initial. And we don't know y final. We don't know how far below the ceiling we are. But if we set it up like this, then whatever we get for y final is our answer. That will be how far below the ceiling it is. The thing is, though, we don't want to have two unknowns in one equation. We want to be able to have some relationship between x final and y final that will describe that allows us to substitute to get just one unknown variable. So let's take a close look at how we would do that. If we zoom in on this final situation, in fact, let's ignore the box entirely. Let's just look at the spring. If we compare the equilibrium distance, 0.5 meters, when the spring is 0.5 meters long, we consider x to be what value?
At equilibrium, right? X naught.
And what is the
Or
value?
0 in that case.
Yeah, x is just going to be 0. So when the spring is equilibrium length, we consider x to be 0 because x is the distance away from equilibrium. But if we have moved to a new location, if we have compressed the spring, x is now non-zero. And let's take a look at how these are related, because we want to establish a relationship between x and y. When x is 0, what's y? What's the how far below the ceiling are we?
Y would be negative 0.5, right?
Right. So when x is 0, when it's uncompressed, y would be negative 0.5. But now x is compressed some distance. X represents how far this has been compressed. So x would specifically be this distance, how compressed it is. And if you know it's compressed some distance x, how would you find the new value of y? If you push this, if you started off 0.5 meters below the ceiling and you push it up a distance x, now how far below the ceiling are you?
0.5 minus x.
We want to treat this as distance below the ceiling, though, so we want to treat it as negative. If you start at negative 0.5 and you go up by x, what's your new value?
So that'd be negative 0.5 minus x, right?
Negative 0.5, but which direction are we going?
Oh, we're going up, so then it'd be
Right
plus
down
x.
Yeah, negative 0.5 meters plus x. So the y value is going to be x above negative 0.5 meters. So if we write it in that format, if we say x final is unknown, but y final is negative 0.5 plus x, or specifically plus x final, we've now established a coordinate system that incorporates both of those pieces of information with only one unknown variable, x final. So if we set up an equation, then x final will be the only unknown. We can solve for x final and then add that to negative 0.5 meters to get y final. Any questions on that so far? Then let's try solving this. I think it's safe to treat this as a closed system. We're assuming that we're not experiencing any energy losses to heat or work. So let's set up our conservation of energy equation. We've got our change in kinetic energy plus change in spring potential energy plus change in gravitational potential energy, adding up to 0. And we can fill in our usual formulas for those. Half the mass times change in speed squared plus half the spring constant times change in displacement squared plus mass times gravity times change in height. And if we fill in all the values we have here, we know the mass, 8 kilograms, so 8 over 2 would be 4. And usually I would recommend including units for all of these, but since we know these are all measured in kilograms, meters, and seconds, they're all in consistent units, we know it's all going to work out to joules anyway. So half the mass would be half of 8, so that would be 4. Delta speed squared would be final squared minus initial squared, 0 squared minus 4 squared. Half the spring constant, half of 800 would be 400. Change in x squared, that's x final squared minus x initial squared. X final is unknown, but x initial would be 0. And then mg delta y, m is going to be still 8 kilograms. Gravity, we're rounding off to 10. Delta y would be y final minus y initial. So final, negative 0.5 plus x final minus initial, minus negative 0.8. So there's our delta y, final minus initial, final negative 0.5 plus x minus initial negative 0.8. Any questions on that setup so far? So if we simplify this, we got 4 times 0 squared minus 4 squared becomes 0 minus 16. So 4 times negative 16 would be negative 48. Then we got 400 times x final squared. And then 80 from 8 times 10 multiplied by, and what can we combine here?
Negative 0.5 and positive 8.8.
Yeah, because minus 0.8 becomes plus 0.8. Positive 0.8 plus negative 0.5 would be positive 0.3 plus x final. And then we can distribute this. 80 times 0.3 would be 24 plus x final, or plus 80 x final. Plus 400 x final squared. And then a minus 48. And the 24 and the minus 48 would combine into just minus 24. So we end up with 400x final squared plus 80x final plus 24 minus 48 simplifies to minus 24 equals 0. So now we have an equation we can solve for x final. Any questions on the algebra there so far? And how can we solve an equation like this?
You probably have to factor stuff, right?
Yeah, we can factor this, or even if it's not factorable, what else could we use?
Quadratic formula?
This is a quadratic, so we can use the quadratic formula to solve it if factoring doesn't work. Or even if factoring does work, we could just jump straight to the quadratic formula. Before we do, though, I'm noticing these are all multiples of what value?
8.
Yeah, these are all multiples of 8, so we can divide both sides by 8 first. If you divide by 8, 400 divided by 8 would be 50. 80 divided by 8 would be 10. 24 divided by 8 would be 3. So this at least makes the numbers easier to work with. And this might or might not be factorable, but we can always just use the quadratic formula to figure out what the values are. And how many solutions should we expect from a quadratic?
2.
Yeah, there may be 2 solutions here. So let's see what those are. We're going to have negative b plus or minus square root of b squared minus 4 times a times c. c is negative, so that just makes this plus. All divided by 2a. So negative 10 plus or minus square root of, that's 200, 3 is 600, so 700. Yeah, this looks like it wouldn't have been factorable because we're not going to get nice, neat, whole numbers. So, punching that into a calculator, it looks like we're going to get 2 values, negative 10 plus this big thing and negative 10 minus this big thing. So we're going to get a positive value and a negative value. Going back to the original, were we expecting x to be positive or negative?
Negative, because it's getting compressed, right?
It is getting compressed, but we got to be careful about the coordinate system. We were treating x as an upwards motion. We were adding x to y, to the y value in the first place. So we often use the standard that compression is negative and stretching is positive. But in this context, since we treated x as positive, as upwards motion being added to y, we should be treating x as positive here. A negative value for x in this coordinate system would mean hanging downwards instead of pushing upwards. And because of the symmetry in the potential energy graph, it ultimately doesn't really matter whether you treat compression as positive or compression as negative, as long as you're consistent about it. How do we get negative 48? Oh, that's right. 4 times 16 should be 64. I was thinking of 3 times 16. So yeah, thank you. That should be 64. Add that to the 24 and we should get minus 40. So yeah, that should actually be minus 40. Dividing by 8, we get 5. So 4 times 50 times 5. That'd be 4 times 50 is 200, times 5 is 1,000, plus another 100 would be 1,100. So, no, that's right. 4 times 16 should be 64. Thank you for the correction there. So negative 10 plus square root of 1,100 divided by 100 gives us about positive 0.23. And we could also subtract to get another number, but the negative doesn't really make sense here. We were assuming x is how far it goes up. A negative would be how far it goes back down if we assume it's attached to the spring, because we would get oscillations here. But we can ignore the negative value here because we're looking for how far it goes up. So that's x final. The block, by the time the block comes to a stop, it will have compressed the spring 0.23 meters upwards. How do we convert that into an actual distance from the ceiling? If we just found x final, how do we convert that into a y value?
I think we had an equation that related x and y before, right? Y equal negative 0.5 plus x.
So if we just plug in our x final value here, negative 0.5 plus 0.23 meters, that will tell us the final y value. So negative 0.5 plus 0.23 would be negative 0.27. And we were defining y in the first place as how far below the ceiling. So that means that the mass ends up 0.27 meters below the ceiling. Any questions on that? And of course, there are other ways to do this as well. You could set up the coordinate system in different ways. You could treat y as your variable and make a substitution for x instead. You just get a different quadratic, but it would still lead to the same results. So many different ways of calculating this, using different coordinate systems or different variables or different substitutions, but they should all lead to the same physical result, that the object ends up 0.27 meters below the ceiling. Any other questions on that one before we move on? All right, so what else do you want to work on? Do you want to try some conservation of energy or potential energy, kinetic energy graphs, or do you want to work on more of the bond energy and introduction to thermal energy, or what? Graphs? Okay. Let's take a look at some potential energy graphs. And then we'll look into more of the bond energy and thermal energy stuff later. What sort of graphs do you want to work with? Including E-thermal? They really shouldn't include thermal energy on these graphs. That's a very bad idea. So sometimes they do anyway.
There was this one quiz on the practice files that had KE rotational, and then they gave us an equation, and then they asked us to plot translational KE and then potential energy due to gravity and
Okay. Do you have a copy of that you could send me as a PDF or screenshot in the files section?
I could try, yeah. Give me 1 second.
And generally, no matter how many types of energy are involved, it's the same overall process. You want to figure out if you know all the types of energy except kinetic energy, then, and you know the E total value, then then kinetic energy is just whatever's left over after you subtract all the other types of energy from E total. So if you know all the types of energy except for one, and you know the total energy, you can find that last missing energy. And the graphs may end up looking very different, but it's the same overall process. Figure out how much energy is left. And if you have multiple types of energy, that can look kind of different. So far we've been looking mostly at just one type of potential energy, and then also kinetic energy. But if you have something like, let's say there's two types of potential energy. For example, maybe you're dealing with spring potential energy and gravitational potential energy. Gravitational potential energy would just be a line because it's just mg, let's say this is y.
I've sent the file in the chat.
Okay, I'll take a look at that. With the spiral rolling down the ramp.
Yeah, that's the one.
Okay, let's pull that up as well. Before we get to that though, if you do have two types of energy, like let's say you also have, for instance, let's say you throw this object upwards and then it hits a spring and starts compressing it. Of course, it's not going to, the spring isn't going to kick in until the object actually hits it. So if we look at a situation like the one we were just examining, if you got the object moving upwards and then it starts compressing the spring potential energy is 0 until the object hits it, and then we get potential energy. Presumably being a parabola or a portion of a parabola. So in a case like that, if you know E total, you can just subtract E total values or subtract the potential energy, both of them, from E total and figure out the kinetic energy that's left over. For example, if you find a location where the value of potential energy of the spring plus value of potential energy of gravity equals 0, or sorry, equals E total, then you know the kinetic energy is going to be 0. But let's get back to that example with the ramp. Let me pull that up on share screen. This one here.
Yes.
So for this one, we know the marble is rolling down this spiral ramp. We don't really care much about the shape of the spiral ramp, though. All we really care about is that it's moving along this path. So in this graph, the L-axis, the horizontal axis here, specifically represents the distance traveled along the path. So we're not really caring much about height, except in the case that we know that height is negative 0.2 L. So for every 1 meter you travel along the path, you move down 0.2 meters. Presumably that just represents the slope of this curved path. So we can use that. We can say, when we're setting up our potential energy equation, because I think we want to graph potential energy of gravity, what's our usual formula for potential energy of gravity?
mg delta y.
Yeah, mg times what?
Delta y.
Yeah, mg, or in a sense, we don't really care about delta here. We just want the potential energy. We just write that as mgy. The mass times gravity times the y value. But we don't want to graph energy versus y here. We want to graph energy versus L, which means we can't write this in terms of y. We want to write it in terms of L. But we have this substitution we can make. Everywhere you see y, you can just replace it with negative 0.2 L.
Mm-hmm.
Because the distance traveled can be directly converted into a height. So if we just substitute that in, m times g times negative 0.2 L, then we get potential energy of gravity equals, and we know the mass, 1 kilogram. We're assuming gravity is 10 meters per second squared. Multiply that by negative 0.2 L. And that simplifies to 1 times 10 times 0.2 would be just 2. So negative 2L. So that's effectively our formula for potential energy of gravity. Potential energy of gravity is negative 2 times L. Any questions on that so far? So let's go ahead and graph that now that we have an equation for it. What shape should we expect that to be if we're specifically graphing potential energy equals negative 2L?
It would just be a straight line with a negative slope.
Yeah, straight line, negative slope, and we even know the slope. It's going to be exactly negative 2. And do we have any labels here? Oh, we at least know this is L equals 10 here. So let's put in a data point there. When L is 10, what should potential energy of gravity equal?
Negative 20.
Yeah, when L equals 10 meters, potential energy of gravity equals negative 20 joules, because it's just negative 2 times that distance traveled. So if we put in a data point there at L equals 10, potential energy equals negative 20, we can now draw the potential energy graph, because we know it goes through, what's another point that it has to go through?
0.
Yeah. When L is 0, potential energy is 0. So we can draw a graph from 0, let me make that thicker, from 0, 0 to 10, negative 20. That is our potential energy of gravity graph. So we've got a potential energy of gravity graph. We're given a kinetic energy rotational graph. And what else are we trying to draw in here?
The translation.
Sorry, what was that?
The translational kinetic energy.
Yeah, we want a translational kinetic energy graph. And for that, as I said earlier, we can find the kinetic energy translational by just taking the total energy and subtracting everything else.
Right.
Do we know the total energy here? Did this say anything about total energy up here?
I don't think so.
We do know the initial speed, right?
Yeah.
Initial translational speed is square root of 10 meters per second. So let's see if we can work from there. The initial is square root of 10 meters per second. And we also know its mass. So its kinetic energy is just going to be 1/2 times the mass times the speed squared. So what's that going to equal?
Sorry, 20? Wait, hold on, sorry.
We've got square root of 10 squared, so that's 10. We're multiplying by 1/2.
Or just 5?
Yeah, 5 joules. So that's the initial kinetic energy. That is at L equals 0. So let's put that on the graph as well. Let me line this up properly. There we go. So if we put a mark at kinetic energy equals 5 joules for the starting kinetic energy, or starting translational kinetic energy, we should specify that. That means that there's one location where we know all the types of energy involved. At location L equals 0, we know translational kinetic energy is 5, rotational kinetic energy is 5, and potential energy of gravity is 0. So how would we find E total?
Just add them all up?
Yeah, if we just add those all up, potential energy of gravity plus translational kinetic energy plus rotational kinetic energy, we get 0 joules plus 5 joules plus 5 joules, or 10 joules. So we know that the total energy at the starting point is 10 joules. And assuming it's a closed system, we should say that the energy total is 10 joules the whole time. So what would that look like on the graph?
Horizontal line at 10.
Yeah, we just get a horizontal line at 10. So that is our graph of E total. And now that we know the total energy everywhere and the potential energy of gravity everywhere and the rotational kinetic energy everywhere, we can also calculate the translational kinetic energy everywhere by looking at the difference. For example, if we jump ahead to L equals 10, at L equals 10, we know that the potential energy of gravity is negative 10, or no, sorry, negative 20. Rotational kinetic energy is given as 10. And we know E total, we don't know kinetic energy translational, but we know they have to add up to 10 joules. So what would translational kinetic energy have to be to make these three values add up to 10 joules?
20.
What was that?
20?
Yeah, should be 20, because that way negative 20 plus 10 plus 20 adds up to positive 10. So we know that at the 10 meter mark, kinetic energy has to be 20. So we can put a mark there. And we have now two data points. In between those, what shape should we expect kinetic energy graph to be?
Just the straight line from 5 to 20.
Yeah, why should we expect a straight line here? I mean, why would we expect kinetic energy on this graph to be a straight line instead of a parabola or a sine curve or exponential or any other shape?
Yeah, because of.
What was that?
I'm not sure actually.
Well, how do we calculate the kinetic energy in the first place here? Like, how do we get that 20 for kinetic energy translational?
We added up all of this, all of the energies, and then subtracted it from E total.
Yeah, translational kinetic energy is just E total minus all the other ones. So E total minus potential energy of gravity minus rotational kinetic energy. E total is a constant, but what do you notice about the shapes of the potential energy graph and the rotational kinetic energy graph?
They're also straight lines.
Right. And if you add functions that are straight lines together, the result will also be a linear function.
Right.
And then if you just add a constant, all that does is shift it. So we should expect the kinetic energy graph to be a straight line because the other graphs that are combined to create it are also linear functions. So it is safe to assume here that this kinetic energy graph will be a linear function. And if you have 2 points, that's enough to define a straight line. So that should be our translational kinetic energy graph. Any questions on that? And someone was asking E total shouldn't go past 10. E total, I mean, this problem is restricted to just values between 0 and 10, but E total is 10 joules for the whole problem. So it's not like there's a reason why we have to stop the graph at 10 meters. I guess physically we might say 10 meters is the bottom of the hole. So after L equals 10, then there's no reason to continue. But if the hole went deeper, then the E total would still be 10 meters. And why is potential energy 0 at initial? Essentially because we're treating ground level as height 0. So if ground level is height 0 and you're starting at ground level, you start with 0 potential energy. And then once you go underground, you now have a negative amount of potential energy. You can also see that from the equation we were using to calculate potential energy, this one right here. The potential energy is negative 2L. If you plug in 0 for L, you'll get 0 for potential energy. Any other questions on that so far? And it looks like the one other question this is asking is, what's the force of gravity along the path? at L equals 10. Well, if we have a potential energy graph, how do we calculate force based on that? Yeah, the potential energy slope tells you what the force is. The force is specifically the negative slope of potential energy, negative derivative of potential energy. So if we can find the derivative of potential energy, that tells us how strong the force is, and the force is in the opposite direction. So looking at our potential energy graph, what is the slope of that graph?
-2.
Yeah, slope is, looks like -2 the whole way. So the slope of this graph everywhere is -2. If it was a curve instead of a straight line, we'd have to be careful about how the slope changes. We'd probably want to take the derivative of the function. In this case, if we just took the derivative of -2L, we just get -2 anyway. So the slope is -2 everywhere, which means the force is going to be what?
Two. 2 Newton.
Force should be, yeah, +2. So the force is +2 newtons. Positive in the sense that it's pulling the marble in the positive L direction. And then 2 newtons is how strong the force is. And note that the positive direction means we're pulling towards lower potential energy, which is exactly what we should expect. Positive direction, so if we actually drew in the force arrows here, we'd have arrows pointing in the positive L direction, and they'd all be the same length, because we have the same slope everywhere on this graph. So those would be, that's one way we could draw the force on this graph. We could draw arrows representing a pull in the positive L direction along the path. And the strength of that would be 2 newtons. Even if the force is negative, yeah, a negative force just means it's in the negative direction, whatever component we're talking about. So if we're talking about vertical motion, for instance, a falling object, let's say, a negative value for that for the force of gravity, if we're talking about vertical motion, would mean a downwards force. In this case, the force is positive the force is in the positive L direction, which basically means forward along the path. If we go back to the diagram of the path in the first place, positive would mean forward along the path, which does mean downhill. We're treating forward along the path, that is slanted downhill, as the positive L direction. So L starts at 0 at the top of the path, and then as we go forward along the path, L is increasing because L represents how far you've traveled so far. So increasing L means you're going downhill. Any other questions on that? Right, either for direction. Yeah, I think so. Since this is just asking specifically for the component of the force, that is how, because the force of gravity is going to be, this was what, a 1 kilogram object? So the actual force of gravity is going to be 10 newtons straight down. But only some of that force is in the downhill direction, along the slope, along the actual path. Like if we take a look at the path itself, the actual path is going to be something like, you've got this ramp, and you've got this this ball rolling down the ramp. The force of gravity is straight down, and it's going to be 10 newtons because the ball has a mass of 1 kilogram. So the actual force is going to be 10 newtons straight down. So that would be the force of gravity. But we're not looking for the actual force of gravity. We're looking for just how much of that is along the ramp. Because notice that this force, the force of gravity, is not along the ramp. It's downwards, not along the ramp itself. what we're doing here is we're splitting up the force into components. We're going to have a component along the ramp and a component perpendicular to the ramp. So the idea here is you can write that force of gravity, instead of writing it as 10 newtons in this direction, you can write it as some amount in the direction along the ramp, plus also some amount straight into the ramp, perpendicular to the ramp. And we're going to look into the idea of splitting a vector into components like that in more detail in 7b. But what we just calculated is just the component along the ramp. So F sub, we might call this F sub L. The force in the L direction is 2 newtons. So we call that the component of the force in the direction along the ramp or along the path itself. Any questions on that so far? And again, we're going to look at that in more detail in 7b, the idea of splitting a vector such as a force into components. If you want to get some advanced practice on that, go to math.ncheese.org, click on Physics 7b, and there should be a couple of practice worksheets on trigonometry review and vector addition. So you might want to try those out just to get some review ahead of time, sometime before Physics 7b starts. Any other last minute questions before we go? All right, then that's it for today. Feel free to email me if you have any other questions. Don't forget to vote. This is a very important election, so make sure you participate in it. So vote, study, and get some rest. Tomorrow morning is going to show up faster than you realize, so get to sleep early. You do not want to go into a midterm exhausted. Good luck, and I will see you next time.